Do you remember the big headlines 3 years ago when the National Ignition Facility announced they'd reached nuclear ignition with their laser shots? Well, they just broke their own record, reached the biggest fusion gain ever, and no one noticed. If someone shoots a laser in a lab and no one reports it, does the weeping press team make a sound? But it was a remarkable shot. And they aren't the only ones who've made remarkable progress in laser-ignited fusion. Let's have a look. Laser-ignited fusion uses what's called inertial confinement. This means that they shoot with the lasers at a target which, due to inertia, can't get away fast enough. So the fuel becomes compressed and ignites, which means it continues burning from its own produced heat. On February 23rd, the National Ignition Facility quietly logged its seventh ignition shot. They squeezed 5 megajoules of fusion energy from just about 2 megajoules of laser light, a record gain of almost 2.5. I think what the NIF does is actually more impressive than what they report, because the 2 megajoules of laser energy doesn't entirely go into the target, only about 15% do. If you take that into account, the gain was actually more than 17, but they do waste a lot of energy with their lasers. The NIF uses a total of 192 laser beams that are focused on a fuel target with a deuterium-tritium mix. To deliver the 2 megajoules to the target, they need to ramp up the laser with an estimated 400 megajoules. If you take this into account, the total gain is just about 0.5% or so. But the NIF wasn't built to be energy efficient. It was built to shoot lasers, arguably one of the noblest purposes any facility can have. But this brings up the interesting question of how much can you improve the efficiency? There are a lot of factors contributing to the efficiency. The NIF pumps their lasers with flashlights. First, there are electric losses and losses in the generation of the flashlight. Then there are losses in converting that flashlight to laser light. Then the laser emits infrared, which needs to be converted to ultraviolet, which brings in more losses. But in the past years, there's been a lot of progress on improving laser efficiency. Diode-pumped solid-state lasers have been able to convert electricity to pump light at more than 50% efficiency for a decade, and the record holders now exceed 80%. The NIF also loses a lot of energy because they don't directly shoot the UV beams at the target. After pumping infrared lasers, they convert the light to ultraviolet, but then they bounce the UV light off the golden walls of the pellet that holds the fuel, and that converts it to X-rays, and that goes into the fuel. That is very inefficient. But last year, the laser facility Omega at the University of Rochester showed that if you skip the final step with the X-rays, you can deliver about 4 times as much energy than the NIF to the fuel capsule. And simulations have shown that if you use the UV laser directly, then that gives you a gain at the pellet of up to 150 or so. That would theoretically be 50 times higher than what the NIF does. There was a lot of numbers, but the bottom line is this. First, just switching to a better laser could get you a huge improvement in efficiency. Using an ultraviolet ray laser could avoid losses during the conversion, and avoiding the X-ray conversion can deliver the energy to the fuel more directly. If you take all this into account, the gain could shoot up above a factor of 10. Even if you take into account that you still need to convert the produced energy into electricity, that should be enough to put power into the grid. And indeed, several startups are working on this, such as the American-based company Excimer Energy. The company Focused Energy recently announced they'll build a test project for laser-ignited fusion in a decommissioned nuclear power plant in Germany. And then there is X-Fusion in Japan, so if Elon Musk ever wants to get the ball rolling, he'll have to think of another name. The Chinese have taken note too. In January, the company Planet Labs released satellite images that show a facility near Myeongyang that looks very much like the American NIF, but about 50% larger. This sounds very promising, but of course there's a reason why the NIF uses this complicated indirect drive with the gold reflections to get the X-rays. It's because it's reasonably robust and not so super sensitive to small asymmetries in the shots and pellet. If you skip this step, you need to be super careful about getting everything in the right place. And eventually there is the question of how much it costs. If producing the fuel pellets is too expensive, it doesn't even matter if you get out net energy. It won't be commercially viable. It'll be some while until nuclear fusion powers the city, but it certainly already powers optimism. The United States is sinking and falling apart at the bottom. I swear this isn't a political statement, it's a geological one. In the past weeks, we have not seen one but 3 different studies that looked at this. I have a brief summary. The first study is quite dramatic. The authors collected a lot of data from seismographs across the United States. From this, they calculated how seismic waves travel through the continental plate and what features this plate has at the bottom. They found that the continental plate, the so-called lithosphere, is crumbling at the bottom and sinking down into the deeper mantle, which is the next layer beneath. It's sinking down in massive drip-like structures that stretch from around 200 kilometers deep, where the lithosphere ends, all the way down to the mantle transition zone at 660 kilometers. And these are just small patches. One of the largest regions where this is happening is beneath Kansas, Oklahoma, Missouri, and parts of Texas and Arkansas. Now, this is geology, so when I say that dripping down, this just refers to the shapes. It's not like watching honey slide off a spoon. These movements happen over tens of millions of years. But the important part is that it's still happening right now. The very foundation of North America is thinning, with chunks of it detaching and sinking down. What's going to happen with this in the future? The researchers suggest that this process could continue to weaken the continental plate. If it speeds up, it might in the long run even cause surface level deformations. This finding is consistent with earlier studies that had already shown hints of big slabs of rock sinking down beneath North America, although those studies used lower resolution imaging techniques. This new research provides a much sharper view, revealing the drip-like structures in detail for the first time. The second study focuses on the Pacific Northwest, Seattle, Northern California, and stretching up to Canada. This region is on top of what's called the Cascadia subduction zone. This is where a small tectonic plate off the west coast, called the Juan de Fuca plate, slowly pushes under the North American plate. This type of subduction is similar to what caused the 2011 earthquake in Japan, which led to the Fukushima disaster. This is not the San Andreas Fault, which is further south and a place where 2 plates slide past each other. In the Cascadia zone, 1 plates are sliding underneath the other, building up enormous pressure, and it's due for a major earthquake. Geological records show that massive quakes of magnitude 8 or 9 happen about every 300 to 600 years in that region, and the last big one happened around 1700. The authors of the new study now use new data and computer models to simulate what would happen if that earthquake were to eventually come to pass, and they found that it'd likely sink the coastline by up to 2 meters in just a matter of minutes. This would very suddenly double the area that's prone to flooding along the west coast. Add sea level rise from climate change, and the researchers estimate by 2100 up to 370 square kilometers could vanish and be permanently underwater. In the third study, things get even more interesting. This one looked at very precise satellite measurements of altitude in 28 of the largest US cities, including Houston, Dallas, New York, and Chicago. They found that at least 20% 90% of the urban areas in all of these cities are sinking, mostly due to groundwater extraction. Basically, the Americans are pumping water out of the ground faster than it can be replaced, and the land's collapsing. In some parts of Houston, the researchers say, the ground is sinking by more than 5 millimeters a year. That might not sound like much, but over a few decades, it's enough to crack roads and damage buildings. All this sounds slightly worrisome, to be honest, but then again, as a European, I'd say, well, at least things are moving in North America. Gravity is not a force. Physicists have been preaching this ever since Einstein came along and told us that gravity is really just the consequence of living in a curved space-time. But maybe we were all wrong. In a new paper that came out just a few weeks ago, a team of physicists proposes that gravity might be a force after all. And if you trust the press release, which maybe you should not, this brings us closer to a theory of everything. I've had a look. In the standard model of particle physics, every force is carried by a particle. Electromagnetism has the photon, the strong nuclear force has gluons, and the weak nuclear force has W and Z bosons. Some people insist the Higgs boson is a kind of force carrier too, and I think they have a point, but I'll let someone else die on that hill. The relevant part is that all these forces in the standard model have force carriers. Gravity, according to Einstein, is not a force. It's a consequence of the curvature of space-time itself. That picture works beautifully for planets and stars, but when you try to use it at the quantum level, it all falls apart. The hypothetical force carrier of gravity, the graviton, stubbornly resists all attempts to fit it into the same mathematical framework as the other forces. The infinities in the equation just do not go away. But the authors of this new paper say we've been thinking about it all wrong. Forget about curved space-time, they argue. Space is flat, always has been and always will be. Instead, they introduce 4 new bosons, one for each direction of space and time. It sounds odd at first. 4 separate force carriers for one interaction? But the idea is that these 4 bosons work together to produce the effects we normally attribute to gravity. When you do the math, they claim the 4 bosons merge and give exactly a spin-2 particle, which is the graviton. But that is not even the most surprising part. They also managed to recover the equations of general relativity, Einstein's own equations, from this setup. How is that possible if space is flat? The trick is something called teleparallel gravity. It's an idea Einstein himself worked on back in the 1920s. Normally, gravity in Einstein's theory is described by curved space-time. Heavy objects bend the space around them. Teleparallel gravity gives you the same effect, but in flat space, by adding something called torsion to the propagation of particles. So instead of curving space, gravity creates little twists and warps that accumulate to produce the same effects. The authors show that their 4 bosons recreate this exact mechanism, and we already knew that this gives us back Einstein's theories, so the math checks out. The biggest claim in the paper is that this formulation avoids the usual problems with trying to quantize gravity. They calculate at least some leading quantum corrections, and the infinities seem to cancel out in a way that doesn't happen with traditional gravitons. This suggests that treating gravity as a force in this way might finally make it compatible with quantum mechanics. That'd be a big deal. So basically what they did was to say we reformulate general relativity in this teleparallel form, introduce force carriers in that different formulation, quantize those, and that seems to work much better. Of course, it's not all sunshine and flat space-time. For one thing, at least the calculation they use in the paper doesn't respect the 4 symmetries of Einstein's theory. This might just be because otherwise they couldn't do the calculation, But I'd be worried that this will lead to deviations from Einstein's theory that are in conflict with observation. They say in the paper that the deviations are extremely small because they're only quantum effects, but I'm not so sure about this. The other issue is that they are a far cry away from proving that this is a consistent way to quantize gravity. Finally, though, there is the complexity. Gravity in flat space, but with 4-gauge bosons, a matrix field to hold phase factors, and torsion instead of curvature. Even if it works, good luck convincing anyone to use it. Then again, it's not like string theory is exactly known for its parsimony, and they could get some thousands of physicists to swallow that. You know me for calling out bullshit theories of everything, but I think this one might actually be a promising new way to look at how to quantize gravity. I also quite like the idea that my videos about how gravity is not a force will one day become historical data. White holes. Think of them as black holes played backwards. In Einstein's equations, you can flip the arrow of time and get a solution that does the opposite of a black hole. Nothing can go in or can stay inside. Everything must come out. For half a century, most physicists filed white holes as a mathematical curiosity. But in recent years, some have argued that they might be a general consequence of black holes. Not only this, but they might make up dark matter, and they could have observable consequences. Let's have a look. First, what exactly is a white hole? A black hole traps anything that crosses its event horizon. Mathematically, a white hole is the time-reversed case. It also has an event horizon, but the temporal direction is opposite to that of a black hole. So nothing can fall in, everything must come out. It's like that guy at the party who doesn't stop talking. However, these mathematical white holes cannot be created. They would just have had to be around since the Big Bang. That doesn't really make a lot of sense. However, this situation changes if you take into account quantum gravity. That is, if you take into account that Einstein's general relativity is missing quantum properties, then this story that white holes would have to be around forever might not be correct. Instead, black holes might eventually all turn into white holes. And black holes, well, those can be created. The idea is that when matter collapses, say after a supernova explosion, it first forms a black hole horizon, but inside the matter never reaches an infinite density singularity. Instead, the collapse rebounds, creating something that very much resembles the mathematical white hole. So the plot thickens, which in physics means the equations get longer. This idea has been pursued, for example, by Carlo Rovelli and Francesca Vidotto, who say that this is exactly what happens in loop quantum gravity. The collapsing matter reaches a maximum density and then transitions into an expanding state, so a white hole. A paper that appeared just the other week supports this idea. The authors don't use loop quantum gravity, but instead unimodular gravity. Unimodular gravity is an alternative way of writing general relativity that just gives you back Einstein's theory. However, if you look at the quantum properties, these are much easier for unimodular gravity. This is why many physicists think that maybe unimodular gravity is actually correct, or at least more polite to the maths. In the new paper now, the authors show that if you quantize space-time in this unimodular gravity, you also get a black hole bouncing to a white hole. Though I have to add that the black holes they looked at are not spherical, but the horizon is a flat, infinite plane, not a sphere. These things can't exist in our universe, but they're mathematically easier to treat, which is why they make a nice test. It's quite possible, I think, that this result will carry over to our normal spherical black holes. So this gives support to the idea that black holes can turn into white holes. And in another paper that just appeared, the authors say we should look for evidence of white holes, and they know how. The transition from black holes to white holes is a violent event that distorts space-time. This, they say, emits gravitational waves with a very characteristic frequency spectrum. They say that this should be possible to pin down by a combination of gravitational wave measurements in the low frequency range, for example by the future LISA mission, and by matching B-mode patterns in the cosmic microwave background polarization. Though this would only pick up on white holes that formed in the early universe, it made them an observational target for the first time. By the way, this video comes with a quiz that lets you check how much you remember. Carlo Rovelli and Francesca Vidotto used to argue that the black hole to white hole transition generates a type of fast radio burst. A fast radio burst is an extremely bright flash of radio waves that lasts only a few milliseconds. They were first identified in the data in 2007, so they're real. Rovelli and Vidotto predicted that the radio bursts, at least some of them, should also come with a gamma ray burst. Alas, that turned out to be not the case. Indeed, by now the fast radio bursts are better explained by flares from neutron stars with strong magnetic fields. In recent years, Rovelli and Vidotto have therefore changed course and now claim that loop quantum gravity doesn't predict white hole explosions after all. Instead, the white hole emission is incredibly slow. This would mean that if small black holes were formed in the early universe, they would shrink from evaporation, turn to white holes, and then continue to sit around for some 100 billion years or so. That is, they would be dark matter candidates. Though if Rovelli and Vidotto are correct, then you wouldn't see them with gravitational waves. Okay guys, you know me, I don't believe any of this for a femtosecond, but I want you to know what's going on in these research areas. I have to admit that I quite like the linguistic twist that dark matter would be white holes. But today I'm convinced dark matter is the weight of alien souls that accumulate in the ether. Hold on while I submit to nature. Thanks for watching. See you tomorrow.